Hello, hello, hello. All right, we are on to chapter 10, learning a new flavor of t-test. And this is going to be for the next two lectures. So at some point in the middle, if you want to stop this lecture and pick it up again on the second day of the scheduled class, that's not a bad idea because, again, there are just, a handful of topics in this class that it's worth kind of slowing down a little bit, making sure that you understand all the concepts. So what should we know so far? Well, at this point, you should know how to evaluate the significance of a treatment effect when we know the population standard deviation. And if we know the population standard deviation, we would run a one-sample z-test to do a hypothesis test on that data. But you should also know what to do if we don't know the population standard deviation. And in that case, we would run a one-sample t-test. That's what we learned in chapter 9. So chapter 8 and really chapter 7 focused on a one-sample z-test, whereas chapter 9 focused on a one-sample t-test. And again, we run a z-test if we're comparing a sample mean to some sort of hypothesized population mean, and we know the population standard deviation. However, if we're comparing a single sample to a hypothesized population mean, and we do not know the population standard deviation, then we'd run a one-sample t-test, and we would use the sample standard deviation as a stand-in for our population standard deviation that we don't have. So by comparing the mean of the one sample to a hypothesized population mean, we can draw conclusions about the population from which that sample came from, right? The likelihood of our sample, if the null hypothesis were true, allows us to make a decision about our test statistic, right? Whether we reject or fail to reject the null hypothesis. Okay. So the hypothesis test that we have done so far allows us to test whether a particular sample is statistically different from some sort of hypothetical population mean. In other words, some sort of other number that's out there, right? And we've done a number of different examples using this idea, right? We collect a sample, we run a test statistic with the intention of comparing that sample mean to some external value. And typically, we've been referring to it as a population mean or a hypothesized population mean, right? Now, this is a very useful design, right? But there are lots of other interesting and important research questions that we just simply can't answer with a one-sample test. So there are many different ways in which an experiment can be designed. For example, all participants can be tested under each of the treatment conditions, or a different group of participants can be used for each one of our treatments. So in a between subjects design, and I want to stop here for a second. Note here, it says between subjects, independent measures, independent samples. This is one of those times in psychology where we use three different terms, and they all mean the same thing. So in a between subjects design, or an independent measures design, or an independent samples design, right, because they're all the same, participants take part in either the experimental condition or the control condition, but not both, right? So again, participants take part in either the experimental condition or the control condition, but not both. So you have a different group of participants are used in each condition of the independent variable. So I don't know, hypothetically, we could be interested in a question like, do men and women differ in their attitudes towards healthcare reform, right? And we'd collect a sample of men, and we would collect a sample of women. So you see we have two different groups. And we might give them a questionnaire about their attitudes towards healthcare reform. Or maybe we're interested in whether depressed individuals spend more or less time on the internet than non-depressed individuals, right? So again, we have two groups. One group has a diagnosis of depression. The other group does not. But the point here is that these groups are unique. They're made up of unique participants. Participants are either depressed or they're not depressed, but you can't be both, right? So you're in one group or the other. Another design is something we refer to, again, there's three terms for it: within subjects, repeated measures, or related samples. So in a within subjects, repeated measures, or related samples design, each participant takes part in all conditions, right? So you have a single sample and you measure it at least two times if you're doing a t-test, right? So we could measure anxiety scores before and after 6 weeks of therapy. We could test whether students feel more anxiety the day before an exam or immediately after completing an exam, right? In both of these cases, we're using one sample and we're testing them twice on two separate occasions. Now this chapter 10, that's going to focus on t-tests for between subjects or independent measures or independent samples, right? The next chapter 11, is going to deal with the within subjects, repeated measures, related samples type of design. But again, just to be specific, you may hear me use these terms interchangeably, depending on what class you're taking, what textbook you're reading, or even a journal article, right? A research article, that's been published in the record. You may use any of these terms sort of interchangeably. So understand that between subjects, independent measures, and independent samples means that for each condition we have a separate group of participants in that condition. For a within subjects, repeated measures, or related sample means we've collected one sample and they're experiencing all levels of our manipulation. So they're in all conditions. All right. Today we're going to be dealing with two samples, right? So we could look at two samples that differ on a particular variable, right? So we could look at males compared to females. We could look at smokers compared to non-smokers. Low socioeconomic status compared to high socioeconomic status. Or we could look at two samples that differ because one has been assigned to a treatment and the other has been assigned to a control group, right? So maybe asking, does a certain therapy or drug reduce symptoms? So, with two samples, we're now going to have potentially two sample sizes, although they could both have the same number of people in each group. We'll very likely have two separate means, 2 degrees of freedom, two sums of squares, right? So you're going to have all of these things that we've been computing for one group. You're now going to have them for two groups. And I want to reiterate here something that I've been saying repeatedly over several lectures. The fundamental procedures that we've been using for hypothesis testing in the past, right, particularly in chapters 8 and in chapters 9, they're going to remain the same. We're still going to state our hypotheses. We're still going to determine our decision criteria, all that stuff, right? Steps 1 through 6, right? They're all going to be the same 6 fundamental steps. But that being said, there's going to be a few aspects of these steps that are going to be a little bit different. And so for the first one that jumps out is how we state our hypotheses are going to be a little bit different. So now we have two samples, right? We want to know whether the populations that they come from are the same or are they different. So let's just start off with a two-tailed test, right? So the null hypothesis simply states that there should be no difference between the sample from population 1 and the sample from population 2. So the difference between sample 1 and sample 2, if we were to subtract them, should be equal to 0. Right? And that's what you see stated in this first example of how to state the null and the alternative, right? So in other words, there should be no statistical difference between our samples. Conversely, right, the alternative hypothesis would say, well, if you take the difference between sample 1 and sample 2, that difference is going to be not equal to 0, right? I mean, sample 1 could be greater than sample 2 or vice versa, but what we're saying is that there's some difference between sample 1 and sample 2, and that difference isn't 0. It could be greater than 0. It could be less than 0. Now, I want to draw your attention to something here that's very important. These are both examples of how you would state the null and the alternative hypothesis, but they're just a little bit different from one another. And both of these not mechanisms, that's not the word I'm looking for, but both these methods are allowed under APA, right? So you could say mu1 minus mu2 equals 0 for the null, and mu1 minus mu2 is not equal to 0 for the alternative. Or you could state the null and the alternative this way. For the null, it would be mu1 equals mu2, and for the alternative, it would be mu1 is not equal to mu2. Now, the only thing that I will stress is you can either do it like this, or you could do it like that, but don't interchange them, right? So don't state the null this way and the alternative this way and vice versa. Pick whichever one you want to do, and then that's the way you do it. But the key thing that I want to get you to understand here is that the null hypothesis is simply saying that there shouldn't be a difference between the mean of sample 1 and the mean of sample 2, right? That difference should be statistically 0. Okay. Now let's talk about the one-tailed test. And this or is not the same as this one, right? Here I'm showing you two distinct different ways that you can state the null and alternative for a two-tailed test. This is the way you would state the null and the alternative if it was a greater than alternative prediction. And this is the way you would state the null and the alternative if it was a less than prediction, right? So let me expand on that a little bit more. For a one-tailed test, right, just like our previous hypotheses test, the alternative can only be less than or greater than, right? Whereas the null would be the opposite, right? Either less than or equal to or greater than or equal to, right? And again, what we're simply still saying in the null is that the difference between the sample from population 1 is really no different. We're saying is less than or equal to, but is really also the same way as saying really no different than the sample from population 2. Whereas the alternative, right, the difference between the sample from population 1 is greater than the sample from population 2, or the reverse, right? So, these are the way you would state the null and the alternative hypothesis if you were doing a one-tailed test. And I think the strategy that we've learned before in the past remains the same. If you determine that the scenario you're reading is a one-tailed test, then I think the logical thing to do is determine what is the direction of the alternative hypothesis. Is it a less than or a greater than direction? And state the alternative first, and then note that the null is simply going to be the opposite of the sign with the equal to. And here, note another thing. I've got numbers as subscripts here. You can do that. That's fine. Typically the subscript measures or abbreviates rather the dependent variable. One of the things that a lot of people do, and sometimes I do this as well, is state test 1 the mean of sample 1 and the mean of sample 2. These subscripts as descriptors of the individual levels of the factor. And you'll see that, the levels of the independent variable. You'll see that when I get to an example. Okay. So then the next step is to determine our decision criteria. The good news is we're still going to continue to use our t-table, and we're still going to select our column based on whether or not we're running a one or a two-tailed test, and whatever our alpha level is. So remember, we determined in chapter 9, we had to ask, was this a one or a two-tailed test? And if it was a one-tailed test, we used this row. If it was a two-tailed test, we used that row. Then we would find whatever our alpha was. So let's say it was a two-tailed test with alpha of 0.05. Then that would tell us that we're going to use this column to find our degrees of freedom. The only thing that remained was figuring out, well, what was our degrees of freedom? Whatever that degrees of freedom is, we would just match it to our column for our alpha and our proportion either in one tail or two tails, and that would give us our critical value. The difference between independent samples t-test and just a regular one sample t-test is that now we're working with two samples, right? And because of that, we have to take into account that we have two different sample sizes. And we're going to need to take that into consideration as we're finding the degrees of freedom. Now we're going to find something that we sort of refer to as the degrees of freedom total typically. So each sample, right, of our two samples, each of our samples is going to have its own degrees of freedom, n minus 1, right? We're going to sum the degrees of freedom of both samples, there's the formula right there, in order to find our total degrees of freedom. So the critical value, let's say we had a one-tailed test with an alpha of 0.05, and let's say one sample has 7 people, and the other sample has 5 people. What would be our critical value? Go ahead and pause the video, see if you can figure it out, and I'll work that out with you on the next, or not on the next slide, but just when you come back. Sorry, I had to take a sip of soda. Sorry for the dead space. Okay, what were we asking? One tail test with an alpha of 0.05. All right, so we'd find our one tail in proportion to one tail row. We'd go to our alpha of 0.05, and we know that our T critical is going to be in this column. Now, because we have two samples, we have to find our combined degrees of freedom. The first sample had 7 people. The second sample had 5 people. So really, the degrees of freedom formula is the sample size of sample 1 minus 1 plus the sample size of sample 2 minus 1. So 7 minus 1 plus 5 minus 1 is going to give us a degrees of freedom of 10. So we'd go over here to the degrees of freedom of 10. We'd go all the way across until we found 0.05 and 1 tail. And the value at that space is a T critical of 1.81. Let's try one more. What's the critical value for a two-tailed test with an alpha of 0.01 if one sample has 8 people and the other sample has 6 people? Pause the video, see if you can figure it out. Okay, so we have a two-tailed test, right? So we're going to use this row right here. We said our proportion in both tails was 0.01. So there it is. This is going to be the column that we use. And one sample had 8 people. The other sample had 6 people. So our formula for the degrees of freedom total is 8 minus 1 plus 6 minus 1. So that gives us a degrees of freedom of 12, which you can find right here. And if we go all the way over to the end of the table, we get a T critical value of 3.055. We could round up to 3.06. So that's the way you find the critical value at step 2. Okay. Now, here's the test statistic, and it looks a little bit complicated. I'm going to sort of tell you before we go through all this that ultimately you're going to be able to ignore this mu1 minus mu2. So keep that in mind, right, as I'm explaining this, that ultimately your test statistic is nothing more than the mean of sample 1 minus the mean of sample 2 divided by your estimated standard error of the mean, which is going to be a new formula. It's going to be different than what we learned in chapter 9. And the reason why it's going to be different is because obviously this is a different test. Okay. So now that I've said that, let me backtrack, and it's kind of worth it to talk a little bit of theory here. Remember that basically with all the one sample tests that we've learned, we've been taking some sort of sample statistic, right? Typically some sort of sample mean. And we've been subtracting from that, typically our hypothetical population mean or an actual population mean. And we've been dividing that by the standard error of the mean or the estimated standard error of the mean if we're doing a one sample t-test. Now we have two sample means. And with those two sample means comes two hypothetical population means, right? Now again, this might look a little complex, but if we consider it in its parts, it's just really kind of an extension of an idea that we learned in chapters 8 and 9, right? So we're really describe what this means, right? In the numerator of this test statistic, we're looking at an obtained difference between the actual difference between our two sample means and the hypothesized difference between our two population means. Again, this isn't as scary as it looks. What's the hypothetical difference between the two population means? As you're thinking about the answer to that question, think about what the null hypothesis is, what the null hypothesis predicts for a two-tailed test if the null is true, right? Then the hypothesized population mean of sample 1 minus the hypothesized population mean of sample 2, if the null is true, right, should equal what? 0. Remember, we start from the assumption, right, that there's no effect between means, right? The null hypothesis, remember, it's always our default position. So this means mu1 minus mu2 will always equal 0, right? Now this will simplify the numerator quite a bit when we actually go to compute t, right? This means for our numerator, what we're really doing is subtracting mean 2 out of mean 1 minus 0. Every time this is 0. So we don't even need to include it, right? For all intents and purposes, we can just ignore this last bit after the mean 1 minus mean 2. So all we're really doing is taking mean 1 minus mean 2, and we're dividing it by some sort of estimated standard error of the mean, all right? Now that's great, right? Look, even if you can't wrap your head around sort of the theory as to, why this little bit here reflects the prediction of the null hypothesis, don't worry about it. Just commit it to memory, right? Before we actually do some practice here, I want to take a little bit of time to talk about this new estimated standard error of the mean term, because it's a little bit more complicated than the previous example. So first of all, let's just recall what the standard error is, right? It's the measure of sort of how much distance or dispersion we could expect by chance between our sample statistic and a corresponding population parameter under this assumption that the null hypothesis is true. So here, our sample statistic is the difference between two sample means, and our population parameter is the difference between our two population means, right? And what the estimated standard error is asking is, how much error can we expect between these two sets of differences, right? Now, normally, to find the standard error, we would take that standard deviation, right, and we would divide it by the square root of our sample size, right? But now, because we're dealing with two means, we're going to compute the pooled sample variance for both means, and we're going to use that pooled variance to compute our estimated standard error. And here is the equation. Now, because we're working with two samples, we need to incorporate the standard deviation or variance, right? Variance of both of our samples into our standard error measure. And the way we do this is by calculating what we call the pooled sample variance. So what we're going to do is take the sum of squares of sample 1 plus the sum of squares of sample 2. And whatever that is, we're going to divide that by the degrees of freedom for sample 1 plus the degrees of freedom for sample 2. Now note that this is the same thing, in your denominator here. This is the same degrees of freedom value you would have found in step 2 when you were looking up the t-critical value in your table, right? And once we know this pooled variance, right? Once we know this pooled variance, what we can do is plug that into the estimated standard error equation for the independent samples t-test. And that's this little monster right here, right? Again, it's not as bad as it looks. We can plug in the pooled sample variance as well as the sample size for each sample into this estimated standard error of the mean equation, and then compute that estimated standard error of the mean that we're going to need to compute our test statistic, right? So what we're going to do is find the square root of the pooled variance divided by the sample size of sample 1 plus the pooled variance divided by the sample size of sample 2. Now, my suggestion for doing this equation is to break it up in pieces. So what I would do first is I would divide the pooled variance by sample size 1, and I'd write that number down. And then I'd divide the pooled variance by sample size number 2, and I'd write that down. Then I'd add them together, and then I'd find the square root of whatever that sum is. And note, this pooled variance is always going to be the same in both of these little fractions that are under the square root function, right? So anyway, once you figure this out, right, this value is going to go in the denominator of our t-statistic, and the difference between our two sample means, mean 1 and mean 2, right, mean 1 minus mean 2, is going to go in the numerator, and then we can compute the test statistic, right? So, it's not as bad as it looks. Okay. And then once we've computed the test statistic, right, we would ask, well, is the difference between our two means large enough that it would fall in our critical regions, right? Here I've got an example of a two-tailed test, but this logic is the same for a 1, right? Just as before, we're asking ourselves, is our obtained t-statistic, the one that we computed in step 3, is it more extreme than the critical t-value that we looked up in step 2? And if it is, we reject the null. If it isn't, then we fail to reject the null. And remember, a t-statistic is a ratio, right? It's the difference between the means, right? If the difference between the means is considerably greater than the difference expected by chance, right, then we'll have a large t-statistic typically. Okay. Now again, if we reject the null hypothesis, then we're going to compute the effect size, right? Remember that what we've learned before in Cohen's d, for the denominator, we've been using the standard deviation. Well, we can find the pooled standard deviation by taking the square root of the pooled sample variance. So let me just sort of point out, when you're at this step and you figure out the pooled variance, make sure you keep track of where this is, right? Because if you reject the null, you're going to need whatever the number is for this equation for Cohen's d, right? In the denominator of the Cohen's d, you're going to find the square root of that pooled variance, which is essentially saying the same thing as the standard deviation of our pooled variance. All right? Okay. Now, our interpretation for Cohen's d, it's just the same as we've learned for other tests, right? You've got that table where you can determine whether it's a small, medium, or large effect. You can also multiply it by the standard deviation, and you can see in exact units what the effect size is. Okay, and then finally, step 6, just state your results in plain English using the APA format, right? So, you always start off with, we reject the null hypothesis, then you report your statistical tests, right? And then you compare the means and the, you compare the means. And include standard deviation for each mean if you can figure it out. All right. Oops, I'm going backwards there. All right, now is the time where I would ask if there's any questions. This is a little table taken from your book. It just shows sort of the differences between, how you would calculate the different tests. Okay, let's just jump right into an example here. So a social psychologist studying mass communication randomly assigns 82 volunteers to one of 2 experimental groups. 61 are instructed to get their news for a month from only the TV, and 21 were instructed to get their news only from the radio. After a month was up, all participants were tested on their knowledge of several political issues. So here's the data. The TV group had a sample size of 61. They had a mean of 24 and a sum of squares of 240. The radio group had a sample size of 21, a mean of 26, and a sum of squares of 120. So I want you, using an alpha of 0.01, to test whether either type of news outlet leads to a difference in the knowledge of political issues, right? So go ahead and run through the 6 steps of hypothesis testing. So pause the video. And when you come back, I will walk you through how to get the correct answer. More soda. I've been lecturing all day. Okay, here we go. So hopefully you figured out that this is a two-tailed test. I know I'm not giving you a whole lot of information here, but know that that's the first thing you should try and ascertain is what type of test this is. And notice that I don't have any sort of directional prediction here, right? I'm just asking you to test whether either type of news outlet leads to a difference, right? I'm not sort of insinuating or directly stating that there's a predicted direction that difference should be. I'm just asking you to test whether or not there is a difference. So again, when there's a lack of a specific directional prediction in the scenario that you're working through, whether it's on the homework, a quiz, or on the exam, right, then you treat it as if it's a two-tailed test. And so that's what I've done here. And note that these are the different ways in which you can state. Remember, there are 2 acceptable ways according to APA that you can state the null and the alternative. Oops, okay. Somebody's doing something in my lab. Okay, great, good. That was that alert. Sorry for the distraction. So let me just walk through them. And remember, I said that you could use subscripts to describe the different levels of the independent variable. So what this is essentially saying is the mean sample for the radio group minus the mean sample for the TV group should equal 0. In other words, we don't expect a difference. The null would suggest that we don't expect a difference between the mean sample for the radio group compared to the mean sample of the TV group. Whereas alternatively, mean radio minus mean TV, right, is going to not equal 0. Maybe their knowledge of political issues is better for radio compared to the TV group, or vice versa. Maybe the TV group has a better knowledge of political issues than the radio group. Who knows? There's not a directional prediction. And note, here's the other way in which you could state the null or the alternative. The sample mean for the radio group should equal the sample mean for the TV group, or alternatively, the sample mean for the radio group should be not equal to the sample mean for the TV group. Okay, so now that you know that it's a two-tailed test, you know your alpha is 0.01, right? That makes it easy for you to find which row you need to use to find your t-critical value. And here, a two-tailed test with an alpha of 0.01, you're going to be using this column right here. And remember, our formula for degrees of freedom is the sample size of n minus 1, or I'm sorry, that doesn't make any sense. The sample size for the first sample minus 1 plus the sample size for the second sample minus 1. Here's the sample sizes right here, right? So 61 minus 1 plus 21 minus 1 equals 80, right? So 0.01, two tails combine, 80. We get a degrees of, I'm sorry, not a degrees of freedom, but a T critical value, right? A T critical value of 2.639, right? 2.639. And note, that should be plus minus 2.639, plus minus 2.639, because it's a two-tailed test. And just like you have it right there, oh yeah, so I've rounded it up. Boy, I'm feeling punchy today. I don't understand. Maybe I should have made coffee instead of soda. All right. You're going to want to label these, of course. You're going to want to plot a normalish distribution like I've done here, right? And label where negative 2.64 is and positive 2.64 is. Now, when we run the statistical test, if it falls in these critical regions, right? So in other words, if it's greater than, if our t-test is greater than 2.64 or less than negative 2.64, we would reject the null. Otherwise, if it falls in between these two t-values, we would fail to reject the null. Okay, great. So now it's time to compute the test statistic, and the very first thing we need to do is find the pooled sample variance. So hopefully you took the sum of squares for sample 1 plus the sum of squares for sample 2, and divided it by degrees of freedom for sample 1 plus degrees of freedom for sample 2. If you did that, you should have got 360, right, if you summed SS1 and SS2, and divided that by 80, and that should have given you a pooled variance of 4.5. Now that pooled variance, that pooled sample variance is going to be carried over into the next equation where you actually find the estimated standard error of the mean, right? Where you take the square root of the pooled sample variance divided by the sample size for the first sample plus the pooled variance divided by the sample size for the second sample. And my advice was to do this division problem first, then this division problem, add them up, and then find the square root. And as you can see, that's what I did. Now this is what you could type into your calculator or key into your calculator, or you could type that directly into Excel. You could do the whole thing all in one shot, right? Here's me breaking it up into steps. So 4.5 would go here, and we divide that by 61 because that was the sample size of the first sample. And that gives us 0.0737. 4.5 would go here, and we would divide this by 21, right, which is the sample size for the second sample. And that turns out to be 0.2143. If I sum these values up, I get 0.288. Then if I find the square root of that, I get 0.537. So 0.537 should have been your estimated standard error of the mean. And now it's time to compute our t-test. And remember, it's going to be mean 1 minus mean 2. Again, I included this in here to just illustrate the point that this is always going to be 0. You could go ahead and skip this minus 0 part. You could just go 24 minus 26 divided by 0.537, which is the estimated standard error of the mean. And so you get negative 2 divided by 0.537, and ultimately you get the t statistic of negative 3.72. So now we need to plot that so that we can make a decision. And note that negative 3.72 is less than one of our critical values, our critical value on the low range or the left side of the distribution, which is negative 2.64. It falls into our critical region. So the correct decision here is to reject the null hypothesis. So there is a significant difference between the TV group and the radio group. Okay, great. So now that you have an effect, well, you know, okay, I need to compute my effect size, right? And remember, the formula for the Cohen's d for an independent samples t-test is mean 1 minus mean 2 divided by the square root of our pooled variance. So to compute Cohen's d, you're going to go 24 minus 26, which was negative 2. And you can divide that by the square root of our pooled sample variance, which was 4.5. So you should have got a Cohen's d of negative 0.942. But remember, treat this as an absolute value and round it out to 2 decimal places. So in reality, Cohen's d is actually 0.94. So you have a very robust effect size in this example. And so now you want to state your findings, right? So the very first thing you should state is we reject the null hypothesis. Then you report the t values, right? So t, and in parentheses, the degrees of freedom, which was 80. Equals negative 3.72. That's the statistic that we computed in step 3. Now we need to say something about our alpha, right? What our alpha was and whether or not we rejected or failed to reject the null. Since we rejected the null, we would say p less than 0.01 because our alpha in this case was 0.01. And because we rejected the null, it's appropriate for us to report our effect size. So that is D, Cohen's D equals 0.94. And then you want to say something to the effect of, participants who got their news from the radio, and then state the mean and standard deviation for that, showed greater knowledge of political issues than those who got their news from the television. Note here, though, in both of these instances, I have the mean and the standard deviation. Now let's go back. I have to sort of thumb back here. Did I have that in the original question? I didn't, did I? Note that there's no reported standard deviation. I give you the mean and I give you the sum of squares, but I don't give you the standard deviation. Here's the thing, though. You should have reported the standard deviation. And I'll warn you that if this was a homework or an exam, although that might be a bit too lengthy of a problem to put on the exam, but if you could figure out what the standard deviation for each one of these groups is, so for example, if you can figure out the standard deviation for the TV group and figure out the standard deviation for the radio group, not only should you do so, but you're required to do so. And note, remember what we learned in chapter 4. Remember we learned how to compute the standard deviation. We could do it as long as we had the sum of squares and the sample size, right? So let me go back to where we were. I think go to the next slide. Yeah. So here you have everything you need in the original example to compute the standard deviation, right? If you know your sum of squares and you know your sample size, recall that you can compute your variance by taking the sum of squares and dividing it by your degrees of freedom. Well, for the TV group, the sum of squares is 240, and the degrees of freedom is n minus 1, so 60. If you divide that, you're going to get a variance of 4. Then to figure out your standard deviation, all you do is find the square root of your variance. So to figure out the standard deviation, you take the square root of the variance, which is 4, and you're going to get a standard deviation of 2. Same thing for the radio group. You're given the sum of squares. You know your sample size. So to compute the variance, you're going to go 120 divided by 20, which will give you 6. And to compute the standard deviation, you're just going to find the square root of 6, which equals 2.45. So be on your toes, right? Make sure that you haven't forgot some of the things that we learned in the past, because even though our exams and things like that aren't cumulative, at least in sort of the classic sense, certainly some of the concepts and the equations that you've learned in previous chapters will often be needed in future chapters. And this is an excellent example of how you still need to make sure you remember how we did the things we did in chapter 4, right? You're going to need that not just for this chapter, but many, many chapters going forward. Okay, that's not a bad example. Again, kind of typical time where I would ask if you have any questions. As always, if you have any questions, you can email me. Be sure that you're reading the textbook and you're keeping up on the readings based on what the syllabus says. You should have those chapters read even before you listen to this lecture, because I promise you it will help. I know some of you say, well, the textbook, it's a little weird to read a math textbook, and I understand that. But even a cursory reading, even a less than optimal reading of the chapter, I think will help you to understand things when we get to lecture. That's just my experienced opinion. Trust me, I've taught this class a ton of times. All right, let's move on. Let's do a little bit of practice, right? Again, I think it's, this is our third statistical test that we've learned. And so you should be able to read some scenarios and, be able to identify, at least based on the 3 tests that we've learned, what type of test it is that we're running. So here's an example. Can people accurately identify emotions in people from other cultures? It's known that when adults from the U.S. try to identify the emotions expressed by members of their own culture, the accuracy ratings are normally distributed with a mean of 82 out of 100 and a standard deviation of 4.5. In this present study, 60 adults try to identify emotions expressed by individuals from Indonesia. The mean accuracy of these ratings is 81 with a standard deviation of 5.1, right? So the question you have to ask here is, what type of test should we use? Pause the video really quickly and I'll come back and give you the answer. All right, so the very first question you need to ask yourself in any of these scenarios, even after we've learned the additional t-tests that we'll learn in the upcoming couple of weeks, is how many samples are there, right? And in this case, there's one sample, one single sample. The sample that's been collected here is looking at 60 adults who try to identify the emotions expressed by individuals from Indonesia, right? And that sample had a mean accuracy of 81 with a sample standard deviation of 5.1. Now, the next thing you need to ask yourself is the population standard deviation known or unknown? And the answer to that question is yes, it is known. We do know the population standard deviation. So therefore, what we should be doing is running a one sample z-test, because when we have one sample and we're comparing it to some hypothetical population mean, and we know the population standard deviation, then the correct test to run is a one sample z-test. Now try and state the null and the alternative hypothesis, right? And pause the video, when you come back, I'll show you the answer. So the first thing we need to do is identify whether or not this is a one or a two-tailed test. So let's see, is there any directional prediction in this scenario here? Let's see, can people accurately identify emotions of people from other cultures? When U.S. tries to do it, the accuracy ratings are blah, blah, blah. In the present study, adults try to identify emotions expressed blah, 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 blah. So there's no directional prediction in this particular scenario, so we should assume that it's a two-tailed test. And under those parameters, for a one-sample z-test, this is what the null and the alternative hypothesis should look like, right? H subscript 0 colon, mu, ACC, I'm abbreviating that, means accuracy, equals, right? So our sample mean equals our hypothetical population mean of 82. There it is. 81 would be incorrect, right? 82 is correct. Whereas the alternative would be our sample mean should not equal our hypothetical population mean of 82. All right, here's another example. 100 psychology students are given study materials for the GRE. Half receive 2 books with practice problems and exams for both the verbal and the quantitative sections of the GRE. The other half receive electronic versions of the same material. The company that develops these materials predicts that the electronic version is more effective. The students who had the paper materials had a mean exam score of 1280, and those with the electronic materials had a mean of 1310. So what type of test should be used? Pause the video and I'll give you the answer when you come back. So, how many samples in this particular design? Hopefully you determined there were 2, right? Half received books, the other half received electronic versions, right? So you're either in the book group or the electronic version, but you're not in both groups. So this particular design is made up of 2 separate samples. And at that point, it doesn't matter whether we know population standard deviation or not, right? Like we can exit the algorithm here and we can go straight to the answer, right? Straight to the answer, which is C, an independent samples t-test. This is all it can possibly be. If you've got 2 groups made up of 2 separate samples, as soon as you identify that to be correct in your scenario, there can only be one answer. And that one answer is independent samples t-test, or again, independent measures between subjects. Remember that those terms are interchangeable. Okay, great. Go ahead and state the null and the alternative hypothesis for this scenario. Pause the video and I will give you the answer when you come back. Okay. So do we have a directional prediction in this particular scenario? Well, let's see. There is one, right? The company that develops these materials predicts that the electronic version is more effective, right? So what does that mean in the real world? It means that if we were looking at scores, right, which is what we're measuring here, if we were looking at scores, the developer of the test materials predicts that scores should be higher or greater, right, for students who use the electronic materials compared to students who use the paper materials or the book materials, right? So your alternative hypothesis is what you want to state first, and it should be just like this, right? The mu electronics, so the sample mean for the electronic group, should be greater than the sample mean for the paper group or book group, whatever. Whereas the null hypothesis should be the sample mean for the electronic group should be less than or equal to, right? So the opposite of this sign with the equal sign, less than or equal to the sample mean for the paper group. Let's do one more. A psychologist develops a new measure of depression. Based on the previous research, it is known that among non-depressed individuals, this test has a mean of 55. To determine if this test is sensitive in detecting those individuals who are severely depressed, a random sample of patients who are described as clinically depressed by a therapist are selected and given the test. Depressed individuals should be significantly greater than the population mean. For these individuals, the mean is 58 and the standard deviation is 9. What type of test should be used? Go ahead and pause the video and figure it out. Okay, so again, if thinking about this as an algorithm, the first question you want to ask is how many samples are there? And you should have determined that there's one sample, right? One sample of depressed people that had a mean of 58 on this new measure and a standard deviation of 9. And they're being compared to some population value. Here in this case, the population mean is 55. Now the next question in the algorithm is, do we know the population standard deviation? And note that it's not in here, right? We know the sample standard deviation is 9, but it doesn't give us the population standard deviation. Therefore, since we don't have the population standard deviation, we're going to be using our sample standard deviation as a stand-in, and that means the type of test we're going to run is a one-sample t-test. All right, and just like before, go ahead and pause the video and figure out the null and the alternative hypothesis. So again, ask yourself if there's a directional prediction, right? And here we've got it right here. Depressed individuals should be significantly greater than the population mean, greater than the population mean. So that means we expect our sample mean to be greater than whatever this population mean is. And since it's a one sample test, again, my strategy is to do the alternative hypothesis first. And here it is, right? My sample mean should be greater than my population mean, which is 55. Whereas for the null, my sample mean should be less than or equal to my population mean, which equals 55. Here's a couple of good conceptual questions for you too, right? Because I like these kind of questions on quizzes and exams. So which of the following is most likely to produce a large t-statistic? Which one of these answers is most likely to produce a large t-statistic? I'll give you just a beat here to pause and see if you can figure it out. And mind you, like most of my conceptual questions, you don't have to do any math here, right? You don't need to do any math to figure out the answer to this question. Give it a shot. Okay, so let's start off with the process of elimination here, right? What is a standard error? Well, that's the value that's going to go in the denominator of our test statistic, right? Of our t-statistic. So we can think about this conceptually. If I divide my numerator by a large denominator, or if I divide my numerator by a small denominator, which one is likely to give me a large output, right? In this case, which one is likely to give me a large t-statistic? And the answer to that question is anything with a small denominator is going to produce a larger value. Like 1 divided by 1 is less than 1 divided by 0.5, right? 1 divided by 1 is 1. But 1 divided by 0.5, which is a smaller denominator, is 2, right? And the smaller the denominator of a division problem, the larger the answer is going to be. So we can already eliminate A and C. Our answer has to be either B or D. Then the next question is, well, is it a small or a large effect that's more likely to produce a large t-statistic? And you can think about the effect as being the magnitude of the difference between mean 1 and mean 2, right? So really what we're talking about here is what is the size of the numerator, right? It's more likely if my numerator is larger, right? If the difference between mean 1 and mean 2 is larger, then I'm going to get a larger t-statistic than if the difference between mean 1 and mean 2 is smaller. So my effect is large. I'm more likely to produce a large t-statistic. So in this case, the answer is D, right? A small standard error and a large effect is more likely to produce a large t-statistic. Okay. And then with a large t-statistic, which of these scenarios is more likely? If I have a very large t-statistic, am I more likely to reject the null or fail to reject the null? Hopefully by this point, I've really sort of beat a dead horse here pretty good, and you should have determined, oh, it should be A, right? I mean, again, we don't have a value to compare it to, but generally speaking, right, if you have a very large t-statistic, typically anything, beyond 3, right, you're more likely to reject the null because the results of your t-statistic, say if it was 3 or greater, right, is at least 3 standard deviations above the mean. So the larger the t-statistic, the more likely you are to reject the null hypothesis. Okay, great. Let's do, I think, one more example. Maybe there's 2. I don't remember, but we'll see. This one's a little bit more involved, right? So you're going to leave this on pause for maybe long enough for your screensaver to come on. So we'll see how it works. Here it is. So a physics instructor believes that natural lighting in classrooms improves student learning. He conducts an experiment in which he teaches the same physics unit to 2 groups of 7 randomly assigned students in each group. Everything is similar for the groups, except that one of the groups receives the instruction in a classroom that emits a lot of natural light, while the other room uses only incandescent light. Both groups receive a final exam worth 20 questions. So here's the question. Does natural lighting improve student learning? And look what I've done to you here. I've just given you the data. So that means that you need to figure out some things here before you get going, right? You're going to need to figure out the mean of each group. You want to figure out the sum of squares for each group. You want the sample size for each group. You want the standard deviation for each group, right? So you got to figure out all these little basic things that you need to know before you can get started on actually step 3, right? So what I want you to do is do all 6 steps of hypothesis testing, including figuring out all the pertinent details for each one of these conditions. So go ahead and pause the video and give it a shot, and I'll work through the answer with you when you come back. All right. So first thing you want to do is state the null and the alternative. And in this case, you want to ask yourself, was this a 1 or a 2-tailed test? And note that I have this set up as a 1-tailed test. And why is that? A physics instructor believes that natural lighting in the classroom improves student learning, right? So the scores for the natural light condition should be higher than the scores for the artificial light condition. That's just another way of saying greater than, right? So the sample mean for the natural lighting condition should be greater than the sample mean for the incandescent lighting condition. Whereas the null hypothesis is simply the opposite of that with an equal sign. And this is really saying that we expect no difference, right? We expect no difference between the natural lighting and the incandescent lighting conditions. So you've got a 1-tailed test, and the prediction is that natural scores should be greater than incandescent scores. So you got a 1-tailed test, an alpha of 0.05, and you have 2 separate samples, each with a sample size of 7. Well, the first thing you want to do is determine, okay, which row am I using? And this is a 1-tailed test, so you're using the 1-tail row. You're going over to find the alpha of 0.05. So your T critical is going to be somewhere in this row. But now you need to figure out the degrees of freedom. So the sample size for sample 1 is 7. The sample size for sample 2 is 7. So 7 minus 1 plus 7 minus 1 is going to give you a degrees of freedom of 12. And that's going to give you a T critical value of 1.782. And remember, this is a greater than situation. So this can become a little bit trickier now. This is something we need to keep in mind as we're going through step 2. Depending upon the directional sign of your alternative hypothesis for a 1-tailed test, that determines which side of the distribution your alpha, or not your alpha, your critical value goes on. Well, your alpha, by definition, your critical value represents your alpha. So I'm not saying anything incorrect. If your alternative hypothesis sign is a greater than sign, then your critical value, all of your alpha, is going to go on the right side of the distribution, and your critical value, importantly, is going to be a positive number. If your alternative hypothesis sign would have been less than, right? So different than this one, less than. All of your critical area, all of your alpha will go on the left side of the distribution, and your critical value would be a negative value, right? So here, this 1.782, it's one tail, and our alternative hypothesis sign is a greater than sign. So that means, all of our alpha, our entire critical region, is going to go on the right side of the distribution, and that means that our critical value, our T critical value, should have been plus 1.78. There it is right there, okay? Okay. Now we get to step 3, right, where you need to compute the test statistic. And there's a lot of things that you need to do before you get to that point. Well, not a lot, but a handful. It's a little bit more labor intensive than typically our examples are in class. But it's good. It's good to review how to do this, because we're going to do this again in the future, right? You'll do it on homeworks. We'll do it on other examples. So it's important that you remember the things that we learned in chapter 4. All right. So I would use the definitional formula to do this, right? Because I think it's a pretty intuitive way to do it. So in order to do the definitional formula, well, the first thing I need to do is compute my means of each group, right? So if I find the mean of all these scores for the natural light group, I get a mean of 16.71. If I find the mean for all these scores for my incandescent light group, I get a mean of 14. And so what I want to do is find the sum of squares, and ultimately I want to find the standard deviation for each group. But importantly, I need the sum of squares to do my T equation, right? So if you recall, the way we do this is you take the sample mean, subtract it from each individual score, square it, and then find that value, right? So 16, which was the first raw value for our natural light condition, minus the mean of the natural light condition, which is 16.71 squared, equals 0.050. If we keep doing that for the next score, 18 minus 16.71 squared equals 1.66. Keep going for the next score. 14 minus 16.71 squared equals 7.34. And do this for all of your scores in the data set. When you're done, if you add them up, you've computed the sum of squares for the natural light condition. But remember, this pooled variance formula is sum of squares 1 plus sum of squares 2 in the numerator of that particular formula. So you need to do the same thing for your incandescent light group. So the first raw score was 17. If we subtract the mean of 14 out of that and square it, we get a value of 9. The second raw score was 13. So 13 minus 14 squared is going to give us a value of 1. The next raw score was 12. So 12 minus 14 squared going to give you a value of 4, and so on. And if you sum all of those up, you get a sum of squares of 16, right? Now, even though you don't need this for the T statistic, you know you're going to need it when you report the results in APA. So while you're here, you may as well compute the standard deviation for each one of these conditions. And note here, I'm not computing the variance first anymore, right? Like, you should be able to just realize that the standard deviation is nothing more than the square root of your variance divided by the degrees of freedom. Or I'm sorry, your sum of squares divided by your degrees of freedom. So here we already have the sum of squares for the natural light condition, right, which we computed at this previous step, right? And we're going to find the square root of that divided by the degrees of freedom, which is 7 minus 1, so it's 6. And that gives us a standard deviation for the natural light condition of 1.60. Same thing for incandescent light. We've got the sum of squares, which is 16. With an n of 7, we know the degrees of freedom should equal 6. So if I take the square root of 16 divided by 6, then I'm going to get a value of 1.63, right? 1.63 for the standard deviation for the incandescent light group. And again, you don't need this for the T equation. You need, let me go back. This, you need the sum of squares and the degrees of freedom. You're going to need this for step 6 when you report the results in APA. Okay, now we've got everything we need to compute the test statistic, but the first thing we need to do is compute the pooled variance, right? So we're going to take those sums of squares for each one of the groups and add them up, and we're going to divide that by our combined degrees of freedom. So we get 31.43 divided by 12, and that gives us a pooled variance of 2.62. And remember also what I said in the previous example. Don't lose track of this pooled variance, because if we end up rejecting the null, right, and we're going to compute an effect size, we're going to need to plug this value into the denominator of our Cohen's d statistic. So we can't lose track of that value. Once we have the pooled variance, we can use it to figure out our estimated standard error of the mean, right, which is this. This should, by the way, extend all the way over. I have no idea why that isn't, but this whole thing should be under the square root function, so don't be confused here. The estimated standard error of the mean is computed by taking the square root of the pooled variance divided by the first sample size plus the pooled variance divided by the second sample size, right? And like I said, you could do this one, then do this one, and add them together. Happens to be that both of them have the same sample size, right? And it looks, I apologize, it looks like I plugged all of this into my calculator at once, but what I'm doing is taking the square root of 2.262 divided by 7 plus 2.62 divided by 7, and I get an estimated standard error of the mean of 0.865. And again, if I now start plugging things into my equation, once again, you don't have to do this minus 0.0. I'm just sort of really trying to reinforce that, you know, both of these values should equal 0, because that's the prediction of our null hypothesis. But in reality, what we're doing is taking the sample mean of the first group, which is 16.71, minus the sample mean of our second group, which is 14, and we're dividing that by our estimated standard error of the mean that we just computed in the last step. So that's going to be 2.71 divided by 0.537, and that gives us a t-score of plus 3.13. So if we plot that on our curve that we generated at step 2, we see that indeed it is greater than our t-critical value of plus 1.78. We visually see that it falls into our critical area. So our answer is to reject the null hypothesis. So now that we've rejected the null, it's appropriate for us to compute the effect size here. And remember, that's mean 1 minus mean 2 in the numerator. And we're going to divide that by the square root of our pooled sample variance. So don't make a mistake here. Don't just plug the pooled sample variance of 2.62 in here. You have to find the square root of 2.62 in the denominator of the Cohen's d. So 16.71 minus 14 divided by the square root of 2.62 gives us an incredibly robust effect size of 1.67. And all that we have left to do is to state these results in APA format. So we have a statement in the very first sentence that says we reject the null hypothesis. Then we want to report our test statistic. So T, and in parentheses goes our combined degrees of freedom of 12, equals plus 3.13, plus 3.13. P less than 0.05 because we rejected the null hypothesis. Our alpha was 0.05. Or was it? Did I mess that up? Did we set our alpha at 0.05 or 0.01? Oh, I didn't even say. Well, you know what? Like I've said this before in chapter 8, the conventional alpha for a psychology experiment is 0.05. So that's what it should be. Don't worry. In every homework in the exam, I'm 100% sure that I give you the example. But here we'll just use the conventional alpha of 0.05. Or where I said 0.05 somewhere, didn't I? I'm not that dumb. Oh, I said it there, but I didn't tell you when you were... I'm going to just type it in here. Hopefully, that's going to mess everything up. Oh, I'll do it later. Anyway, the alpha should be 0.05. We rejected the null at an alpha of 0.05. And then we report our Cohen's d, which equals 1.67. So scores on the final exam were higher for students in the natural light group. And note I'm reporting their mean and their standard deviation. So remember, that's why I figured out the standard deviation at the previous step. Like I told you in the previous example we did, if you can figure out the standard deviation, which you could from that problem, I gave you all the data, then you have to do it and you have to report it because you should always report the mean and standard deviation, right? So that's 1.60. Compared to students in the incandescent light group that had a mean of 14 and they had a standard deviation of 1.63. Okay, so that's it for this particular chapter. Remember, like I said, you should break this up into two because I've spread this lecture out over 2 days to give you a little bit of time to ask questions if you need to, give a little bit of time to rewatch the video, make sure you've read everything in the textbook. And make sure that you're comfortable with everything. If you need additional practice, here's some questions from the back of the chapter. And note that 15b is a confidence interval question, so you probably don't know how to do that. You've read about that in the chapter. You might not understand it yet because it's a bit more of a difficult thing to figure out. But just remember, if you look in the syllabus, note that I'm going to do all of my lecture on confidence intervals in one day, right? So if after I've done the confidence interval stuff, if you feel the need to go back and practice, you can go back and do question 15b. So that's all that I've got today. Again, if you have any questions, feel free to let me know. Please let me know. Okay, bye.